All right, students, thought I'd try another solution from chapter 5, and mostly because this, the solution in the author's one is mostly correct, I guess. They start off with the right formula, but then they put in the wrong numbers and they get the wrong answers. So I think that's misleading some of you. But if you look at the author's solution, you'll see that he starts off right, the right idea and the right equation, and then puts in the wrong numbers. And so that's kind of interesting. So it's wrong. And even the numbers he puts in then are calculated wrong. Or I should say they. This book's written by a number of different authors. And so whichever author put it in, they that one, whoever that one is, did it wrong. Or maybe they hired someone to do the solutions. Anyways, let me go ahead and read this one. It says, by what factor does the drag force of a car increase as it goes from 65 to 110? Now, the neat thing about this is you're going to see it's an amazingly big number because the drag force is the velocity squared. The pattern of numbers, I don't know if you've ever done this with squares, but 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Look how much they increase. This increases by 3, this increases by 5, this increases by 7, this increases by 9. And so the increase between each of them gets bigger and bigger and bigger and bigger. And so the drag force, and therefore your fuel economy, if this is a car, really can suffer significantly when you go from, say 60 miles an hour to 80 miles an hour, or, I'll pick on 55 miles an hour because throughout the 70s and the 80s during the gas crunch, and maybe we're heading that way again, there was a federal mandate that the maximum speed limit was 55 in every state, and that was designed to save gas. And so it wasted a lot of time driving so slow, but it saved a lot of gas. And that was around for a while, and eventually it got back to let each individual state decide. So, as you know, most of California, at least in the major metropolitan areas, are 65, and then they get out to 70 out in the deserts. Crossover in Arizona at 75. Montana had a 90 for a while, but the federal government stepped in and said that was too much. I think they're down to 85 or something. I don't know. Never been to Montana, so, but they were the biggest in the country. Okay, well, anyways, that's kind of what this is illustrating. So, because it doesn't sound like too much. I mean, if you go from 65 to 110, you're not quite doubling. You're going, 65, I doubled that at 130. I'm not there. And a naive example of this would say, oh, well, it doesn't even double. And that's not quite right. I mean, a doubling would be an increase of 100%, and you're going to see that this is more than that. And yet we still didn't even double the speed because it's that square. So to do it as a percentage, because that's what they say, it says here, it says by what factor. So I shouldn't say percentage. We'll do both. We'll do factor and percentage. By what factor did it increase by? So when they're talking about a factor, we might put here, okay, let's figure out how much did it increase by compared to its, sometimes we'll say its base, or sometimes we'll say what it started at. So maybe I'll do the start at first, because the drag was that 1/2 times the coefficient times the density of air times the cross-sectional area times the velocity of it starting. Let me call that velocity 1 squared. Now, the increase would be a difference. How much did it change by? So this would be a 1/2 times c times rho times a times velocity 2. So that's the new resistance. So that's the bigger one. Minus what it started at. Now, fortunately, a lot of these simplify, and that's why I think the author is writing it this way, that we can get a factor increase or a percentage increase without worrying about things like what is the shape of the object. They would cancel off in both top and bottom. What is the density? Doesn't matter, cancels off. What is the size of the object? It doesn't matter. The 1/2 doesn't matter. So it just comes down to the increased speed, or the new speed squared minus the old speed squared over the original speed. That would be our fraction. And the neat thing about that is they would be the same units. So we could put it in terms of meters per second, kilometers per hour, miles per hour. It doesn't matter. In fact, you see kilometers per hour, and some of you might have been tempted to convert it into meters per second, because we did that a lot when we were doing things in newtons. Not necessary here. Whatever the units are, they cancel off. So it's the same fraction and the same factor. So that's kind of neat. So this will be 110, and I'll square it and just say the units would be then kilometer per hour squared. But I'm not even going to write it down because it's going to cancel off with the units there. So as long as they're all in the same units, we're golden. All right, so then this would be the 65 squared, and there's the original 65. So that would be the factor. So let me go 110 squared minus 65 squared. So there's the numerator. Let me divide that by 65 squared. And so I would say it increased by, the increase by 1.86. And so, again, that's just how much it increased. To give you an idea, so if the resistance was 10, the new would be 10 plus the factor that it increased by, which is almost 2. Now, actually, I'll just multiply it out. That it increased by 18.6. So the increase is actually more than it had to even start with, right? If the increase was a factor of 1, that would say it's double. The increase is, 100% more. But this, it's way more, 28.6. And of course, that's how you write a percentage. So there's our increase by. All right, hope that helps.